Hello friends, welcome back. Let us solve problem set 2. The first problem, in a circle with center P, the chord AB is parallel to tangent. Let us draw this figure. A circle is given. The circle with center P is given. Then the chord AB is parallel to tangent. This is the chord AB and this chord is parallel to tangent and intersects the radius drawn from the point of contact. From this point, when we draw radius at the midpoint of the radius, that means this AB, if you connect this is the midpoint Q. So this equal to this. Okay. Now what they are asked, if AB is equal to 12, find a radius of the circle. If AB is 12, find a radius of the circle. How will you solve this? This is very simple. First of all, our first method is first understand what is given in the figure. So by our method, first let us analyze what we can know from this figure. If this is point R, then if this is tangent, then this must be right angle. Correct? What else we can find out? They are already given that PQ and QR are equal because it is intersecting in the midpoint. Now they are given AB is parallel to R. If these two lines are parallel, then the corresponding angles in the parallel lines are congruent. That means this is also 90 degrees. Correct? If this is 90 degrees, I can simply connect this and this is a right angle triangle. Now, by the property we know that the perpendicular from the center to the chord bisects the chord. That means this equal to this, and AB they are given 12, that means this is 6. Correct? Also, they say that this is bifurcating, this AB is bisecting the radius. So this is R upon 2 and this is R upon 2. Now in this right angle triangle, this is R. So just apply Pythagoras Theorem, that is R square is equal to 6 square plus R upon 2 bracket square. So let us solve this. R square is equal to 36 plus R square upon 4. So very simple. So we have R square minus R square upon 4 is equal to 36, and so we have 3R square, that is 4 minus 1, 3R square upon 4 is equal to 36. So we have R square is equal to 36 into 4 upon 3. So pause your video and find the value of R. That is your required answer. Please do it now. The answer is 4 root 3. R is equal to 4 root 3 units. I am writing units because no unit is given. So you should write the unit there. Very simple example. This was the example number 1. Let us go to example number 2. Let us see example 2. The figure is something like this. Let us read the problem. In the figure, O is the center of the circle and a segment AB is the diameter. This segment AB is the diameter. At the point C on the circle, the tangent CD is drawn. At the point C on the circle, the tangent CD is drawn, and at the point B, tangent BD is drawn. Show that segment OD is parallel to segment AC. This OD is parallel to this chord AC. This we have to prove. Generally, whenever you have to prove the parallel lines, then we have to use the corresponding angle or alternate angle test. Now from this figure we understand that this is the right angle and this is also right angle because both are the tangents and these are the radius. Now here can you see that this angle PCO, this angle and this angle are congruent. Why? Because angles in the alternate segment. These are the angles, this is the segment, and these are the angles in alternate segment So this angle and this angle are congruent. Now, I already told you that this is a cyclic quadrilateral because opposite internal angles are supplementary. Addition is 180 degrees. 90 plus 90, 180. This angle intercepts this arc, and along with that, this angle OBC also intersect the same arc. Angles intersecting same arc, so these angles are congruent. Correct? So, if these two angles are congruent and these two angles are congruent, obviously these two angles are congruent. And now you can say that AC and OD are the parallel lines and PD is a transverse, and so this is the converse of corresponding angles, and hence AC is parallel to OD. This example actually is simple but little bit confusing because here this quadrilateral, that circle is not drawn. That is why it is confusing. So let us understand this problem right from the beginning. The first thing before drawing this cyclic quadrilateral, the first thing is this is the angles in alternate segment. Correct? This angle ABC and angle PCA are congruent angle. So if this is angle A, this is also angle A. Correct? Now this is angle 90 and this is also 90. This angle DCO and OBD are 90. Addition is 180. Angles are supplementary, and whenever in any quadrilateral opposite angles are supplementary, that quadrilateral is a cyclic quadrilateral. That means all the vertices of that quadrilateral lies on the circle. That means there is a big circle passing through these 4 points, out of which I am only drawing this much part. This arc I am drawing. Now in this arc, can you see that this circle is passing through D also, B also, O also, cyclic quadrilateral. So this arc is intercepted by this angle and this angle A both. Can you see OBC and CDO, same arc? Correct? The both are the angles inscribed in the same arc, and so this is also angle A. Here the only hitch is you have to imagine that circle for which this is a cyclic quadrilateral, and hence from 1 and 2, that was the first expression we got, and 1 and 2 we get that these two angles are same or congruent, and now we can state that line AC and OD are two separate lines and PC is transverse, and since these two angles are congruent, so by the inverse of the corresponding angle test of the parallel lines, AC and OD are parallel lines. Okay? The only point in this is you have to imagine that circle which is accommodating this cyclic quadrilateral. So this was the example number 2. So let us go to example number 3 now. The third example of problem set 2 is two circles with centers P and Q touch each other externally at point T. At point T, these both circles are touching each other. Line AB is a common tangent touching the circles in point A and B. This line is touching the circles in A and B. BD is a diameter of the circle with center Q. BD is a diameter of center with circle Q. Prove that DTA, this D, T and A, these points are collinear points. This is what we have to prove. Now here we have to construct something. The first thing we have to construct, I have given you the hint that whenever you see the diameter and point on the circle, just connect that, so that we know that the inscribed angle theorem for the semicircle is 90 degrees. Correct? So this angle is 90 degrees, that we know. Okay? Now whenever two circles are touching externally, generally draw the common tangent here. So here I will draw tangent Let us draw it by some different colors so we'll understand that. So here I am drawing a common tangent. Let us name this point as C. Okay, so two lines I have drawn construction. So one is this, because I know that this is diameter and I got one point external on the circle, so this must be 90 degrees. Now, what else we can find out? We have to show these 3 points are collinear points. What else we can find out from this figure? Can you see that this is also tangent and this is also tangent to this circle? So this line must be equal to this line. And so this angle A must be equal to this angle A. These two angles are same because they are isosceles triangle it has become. Similarly for this circle, tangent segments are common. So these 3 lines are equal and so this is also same angle A. So all these angles are same, correct? Now in this triangle ATB, A plus A plus A plus A is equal to 180. This 4A is equal to 180. That again I am telling you, in this triangle ATB, A plus A plus A plus A is equal to 180. Angle addition. So 4A is equal to 180. So A, or rather we want to find out the 2A. A plus A we have to find out because we want this line to be shown. All these 3 points to be shown collinear. So 2A is equal to 90 degrees. So from here I can find out that this angle is 90 degree. Correct? And by inscribed angle theorem, angle inscribed in semicircle, this angle is also 90 degrees. But since those angles are these two angles are the angles in linear pair ATB and BTD, these are the angles in linear pair, both the angles are same 90 degrees, addition is 180, so these 3 points must be collinear. That is A, T and D points are collinear points. This is we have proved. Let us see problem number 4. The figure is given something like this. Don't look at my figure. It is not very perfect circles. But I'll explain you the figure. There are 2 circles touching inside at point A. This is the smaller circle and this is the bigger circle which is touching at point A. Okay. Now this circle, smaller circle is passing through the center of this bigger circle which is N. Okay. Now from this point, this is the diameter. CA is the diameter of this bigger circle. From this CD, this is the chord of this bigger circle which is touching smaller circle at P. Now they have connected this touching point to the M, that is the center of the smaller circle, and they have connected DA. Let us see what they have asked. First of all, let us see what they have given. M is the center of the smaller circle, its radius is phi. This is phi. So this is also phi. This is also phi. So we have to find out now CD. We have to find out this distance. CD we have to find out. Okay. So first let us understand what we know from this figure. So I can easily understand that this angle is 90 degrees as this is the tangent and this is the radius. I know that radius I know, and this circle is passing through the center point of the bigger circle. That means if this is 10, this is also 10. Correct? Now in this triangle CMP, this is the right angle triangle. You know this side phi, you know this side 15. Can you easily find out the CP by the Pythagoras theorem? It is very easy. So please pause your video and quickly find out the length of CP. Do it now please. CP is 10 root 2. This is what we find. Now, can you see that? Can you see these two triangles? Can we prove that these two triangles are similar, that is CMP and CAD? If we can prove that these two angles similar, then we can easily find out the length here of the CD here. How we can prove that? Very simple. This is right angle and this is diameter of the bigger circle and this is the point on the circumference. So I know that the angle inscribed in semicircle is again right angle. So now in these two triangles, triangle CMP and CAD, these are the right angles and this is common. So by a test of similarity, these two triangles are similar triangles. So pause your video and quickly write down the names of the two similar triangles. Triangles are CDA, that is CDA, I am starting from the common point, CDA is similar to CPM. Both the triangles are similar. So now if these two angles are similar, just write down the ratio, some ratio you write down, and we want a CD. So CD upon CP. CD upon CP is equal to, you can write what you know more in this, that you can write. You know CM. So CM upon CA, or I can write CA upon CM. So we got this relation. CD we know, no, CD we have to find out, okay, this we have to find out. CP we know 10 root 2. CA we know, CA is 20, the diameter of the bigger circle. CM we know 15. So you can easily find out the value of CD. So please pause your video here and find out the value of CD. Quickly, do it now please. The answer is CD is equal to 40 root 2 by 3. If they are given centimeters, then we can write centimeters. Nothing is given, so you can just write units. So you can just write units to this. Have you understood this problem? This is very simple problem. In the circle, you should always expect such a combination of the theorems. Though here you have to use the similarity, here you have to use the inscribed angle theorem, and so on. Let us move ahead and solve the next problem. Problem number 5. Please draw the figure. In a right angle triangle ABC, this is the right angle triangle A, B and C. In the right angle triangle ABC, angle ACB is 90 degrees. This is angle 90 degrees. A circle with the radius R is inscribed in this triangle. That means this circle with radius R is inscribed in this, and we know that when it is an in circle, this is the radius R, this is the radius R. Then they say A, B and C are the length of the sides of BC, AC and AB respectively. A, B and C. So this is A, this is B and this is C. Sides of the triangle respectively, and we have to prove that 2R is equal to A plus B minus C. 2R is equal to A plus B minus C. This is what we have to prove. Let us see how to solve this problem. Since this is an in circle, the sides, all three sides must be touching the circle. That means if this is the radius, it has to be 90 degrees. If this is the radius, it has to be 90 degrees because the tangent and radius at that point are perpendicular to each other. And this ACB is already given 90 degrees. Correct? Now all four angles are 90, that is right angles, and opposite sides are equal. So this is also R, so this is also R, and this is also R. So this is a perfect square. Correct? Now, can you see that this side equal to this side, because this is the tangent segments from external point. This side equal to this side, tangent segments again, and this side equal to this side. So now what is AC equal to? AC equal to this segment plus this smaller one. What is BC equal to? This R plus this. So can we write that? Let us write small letters here. I can write here alpha, alpha, this is beta, and these are the R. We know that. So let us write AC is equal to alpha plus R. BC is equal to R plus beta. So if I add AC plus BC, I will get alpha plus beta plus 2R. These are the names I have given to alpha and beta to these segments. If you want, you can just write, you can mark these points and you can write the names of the segments also. No harm in that. Okay. Now what is AC and BC? AC they are given as B and BC they are given as A is equal to alpha plus beta plus 2R. So I want here 2R to left hand side. So that will become minus 2R is equal to alpha plus beta minus B minus A. Correct? But alpha plus beta is AB and which is nothing but C. So minus 2R is equal to C minus B minus A. I want to eliminate this minus sign. So I will change sign throughout. So I will get 2R is equal to B plus A minus C, which is proved. Simple example. Instead of writing here alpha and beta, you can even write the names of the segments. For example, you can take some points here P, Q and R and then write that AC is equal to AP plus R, BC is equal to R plus RB and so on. And RB is equal to BQ and AP is equal to AQ because tangent segments equal length, are of equal length. Correct? Or you can simply first declare that let us consider these two lines as named as alpha and these two segments length named as beta. Instead of alpha and beta, you can take a small p, small q, something like that. If you give the names to these segments, it will be easy for understanding and easy for writing also. So this is very simple example, but it can become complicated, okay, if you give the names to the segments. So let us see the next example, the example number 6. Now this is the figure given. Let us read the example. In the figure, point P, B, Q are the points of contacts of the respective tangents. P, B and Q are the point of contacts or tangents. That means QA is tangent, AC is tangent and this PC is tangent. Then they are given the line QA is parallel to line PC. Line QA is parallel to line PC. Obviously, when this is 90 degrees and this is 90 degrees, and these two lines must be parallel to each other. Next, if QA is equal to 7.2, if QA is equal to 7.2 and they are given PC is equal to 5 centimeter, PC is equal to 5 centimeters, we have to find a radius of the circle, that is this segment OB, radius of the circle. Now how can we proceed? Before proceeding, let us see what we can understand from this figure. Okay, it is obvious that when this is tangent, it has to be 90 degrees, this is 90 degrees and this is also 90 degrees. Do you remember I told you that whenever you see the 90 degree angle, try to complete the triangle. So here I will make this OAB right angle triangle, I will join OA. Similarly, this is right angle, I will join OC. These two lines are joined. What else we know from this figure? Simple. If these two are the tangent segments, they have to be equal. Similarly, these two tangent segments are equal. If you can prove that this is right angle, then by geometric mean you can say that OB square is equal to BC into BA. That means here we have to prove this is right angle, and then finding out radius is very easy. How can we prove that? Now consider these two triangles. QA is equal to AB. OQ and OB are equal because those are the radius of the circle, and this angle is congruent 90 degrees. So by Sas test of similarity, these two triangles are similar. So these two angles are corresponding angles of similar triangles, so those are congruent. Similarly, we can prove that these two angles are congruent. Simple. These two lines PC and CB are congruent because tangent segments. These two angles are right angles and these two are the radiuses. So by here also Sas test of similarity, we can prove that these two triangles are similar. And now again these two angles are congruent because the corresponding angles of similar triangle are congruent. Now when QP is a diameter and these four angles combines 180 degrees because it's a semicircle, 180 degrees. I will just give names to these angles. We can directly write that. Suppose this is A, then this is also A, this is B, and this is also B. So you can say 2A plus 2B. Here we can say that 2A plus 2B is equal to 180. So A plus B is equal to 90. Now here this is A plus B. So this angle is 90 degrees. A plus B is 90 degrees. So this is right angle. And by geometric mean property, we have OB square is equal to AB into BC. And we know what is AB, we know what is BC, so we can easily find out what is OB. So please pause your video here and find out the radius OB. The OB here is 6 centimeter because 7.2 into 5 is nothing but 36, and square root of 36 plus minus 6, of course the radius cannot be negative, and so we have the answer 6 centimeter. Centimeter is important because everywhere they are given 7.2 centimeter, 5 centimeter, and so on. So this example was not difficult. Only thing, first of all, just understand what you can judge from this figure, and then if at all right angles are there, complete the right angles, right angle triangles, complete the right angle triangles, and then you can use either Pythagoras or geometric mean and you can find your answer. So let us move to next example. Example number 7. Now in this example again a figure is given. They say that if two consecutive angles of cyclic quadrilateral are congruent, two consecutive angles, let us name this cyclic quadrilateral as A, B, C, D. A, B, C and D. And they say that this angle is equal to this angle. Angle B and angle C are congruent angle. Then prove that one pair of opposite sides is congruent. Suppose these two sides are congruent, we have to prove, and the other is parallel, and this pair is parallel. Now the construction I will draw a line parallel to AB passing through D. So let us say that this line is parallel to AB. This is our construction. You have to write what is given and what you are constructing. Write down the construction. Construct DE parallel to AB so that B, E and C are collinear points. So now we have constructed ED parallel to AB, and now ABED has become a parallelogram. Obviously these two opposite sides of parallelogram are equal sides. Now angle B and angle C are congruent, this is given, but A plus C, A and C are supplementary, that means A plus C is equal to 180 degrees. But C and B are congruent angles, so can I substitute B instead of C? Definitely. So A plus B is equal to 180. If A plus B are 180, A plus B is equal to 180, this is a supplementary angle test for parallel lines, and hence AD is parallel to BC, because AB is transverse here and angle A plus angle B is equal to 180, supplementary angles. So one point is proved. Whatever they are asked, one point is proved, that BC is parallel to AD is proved. We have constructed ABED as a parallelogram. So this line and this line AB equal to ED, opposite sides of parallelogram. Now in this parallelogram, if these two lines are parallel, then these two are the corresponding angles, and corresponding angles between the parallel lines are congruent. So I can say that angle, now second part, angle B is equal to angle E. Angle B and angle E are congruent. But angle B is equal to angle C, which is given. So I can say that angle C and angle E are congruent. Now these two angles are congruent angles. And if these two angles are congruent angles, those are the base angles, and hence triangle DEC is an isosceles triangle. So opposite sides of the congruent angles are equal, and hence AB is congruent to DC. Very simple example, I will explain it again. These two, angle A and C, are supplementary angle because their addition is 180, because it is a cyclic quadrilateral. But angle B and C are equal, so A plus B is 180. So this is nothing but supplementary angle test of parallel lines, and hence AD and BC are parallel. This was our first part. So obviously these two angles A and B are supplementary. So by the interior angle test of parallel lines, AD and BC are parallel. And now the second part of it. We have already constructed ED parallel to AB. So opposite sides of parallelogram are congruent, equal. And angle B and angle E are corresponding angles between parallel lines, and hence those are congruent. So I can write that B congruent to E. But we know that B and C are equal. So I can write C equal to E. Instead of B I have written C. So now C and E, these two angles are congruent, which are the base angle of triangle DEC. And hence this is nothing but an isosceles triangle. So the opposite sides of congruent angles are congruent, and hence AB is congruent to DC, and hence both the points are proved. Simple example. Let us go to next example. Problem number 8. The figure is given. Two circles intersect each other in points X and Y. These two circles are intersecting in the point X and Y. The secants through X and Y intersects one of the circle in A and D. The secant through X and Y intersects one circle in A and D and another circle in C and B. And also they have given A and B are on the opposite sides of the line DC. A and B are on the opposite sides of the line DC. Okay. So this information is for drawing the figure. I have drawn this figure. The figure is not given, sorry. Figure is not given, we have to draw the figure. So first of all, how we will draw the figure? Two intersecting circles are there. They are intersecting in X, Y. Then the secants are drawn through X and Y, which are intersecting both the circles. Okay. and they are given that through X it is intersecting A and C, and through Y it is intersecting D and B. And to name these points clearly, they have said that A and B are on the opposite sides of the line DC. Okay, now I have joined XY. What we have to prove? Show that the line AD is parallel to line BC. We have to show that AD parallel to BC. Now, this AXYD is a cyclic quadrilateral because all 4 points lies on the circle of this circle, and CXYB is a cyclic quadrilateral for this circle, smaller circle. Correct? So, this angle A, I will write a small a, angle A, and angle B, I will write a small b, are supplementary angles because opposite angles of the cyclic quadrilateral are supplementary. Correct? Similarly, in this circle, this angle, I will write here small c and D. Small letters, not capital. This D and this D is different. Okay. So C and D are supplementary. Why? Because this is a cyclic quadrilateral. Opposite angles of the cyclic quadrilateral are supplementary. That is, the addition is 180. Correct? Now, this angle C is equal to angle A because this is the exterior angle of the cyclic quadrilateral, which is equal to remote interior angle. So here I have A plus B is equal to 180. Similarly, C plus D is equal to 180. But I know that A is equal to C. Remote interior angle of cyclic quadrilateral. Correct? Now I can just substitute A and D. Instead of D here, I can write C. Correct? So from these two I can write that A plus D is equal to 180. So now from here I know that A is equal to C. So instead of this C, I will write A. And hence A plus D is equal to 180. If these two angles are supplementary, then by the interior angle test of the parallel lines, we can say that AD is parallel to CB. Example is very simple. This example is very simple. The only thing in this example, the figure is not given. Now, if you miss the figure, the description of the figure is given, but actual figure is not given. You have to draw the figure. So many times it happens that the students fail to draw the figure from the description. If you miss this figure from the description, then your problem may go wrong. Because ultimately this actual, when the figure is known, the problem is very simple. But the figure itself is not very simple to draw from the description of the lines. So we will read the description of the lines again. Okay? And we will draw the figure again. They have stated that two circles intersect each other. That means we have to draw first two circles. These two circles you have to draw. These two circles are intersecting each other. Don't look at my figure. My figure is not very good. I am drawing by my hands. And they say that they are intersecting in point X and Y. So this is point X and this is point Y. Some of you may write this is X and this is Y. Doesn't matter. Okay. Now, the secants through X and Y intersects one of the circle in A and D. Now, we have two secants. One of the circle in A and D. And other circle in B and C. Okay. Generally we write like this. We write topper one first and then lower one. But now this figure is wrong because what they say, AB are on the opposite side of line DC. Line DC is here, but AB are on the same side. So here your figure is wrong. Correct? The points are wrong. So it is like this. Point A and B are on the opposite side of DC. So on DC line, they are on the opposite side of this line. See, in this case, even if we have to show that the line AD is parallel to BC. Okay. Now here, even if you don't take like this, even if your figure is like this, you may not miss the answer, only your points will change, the answer will change. Means the name of the points, name of the angles will change. But you should have practice of drawing the figures correctly from the description, because here it's okay, doesn't matter. But in some other figure, you will totally miss the figure and totally miss the answer. Correct? And in this case also, if they have given that the A and B are on the opposite side of the DC, they are specifically given, and you have not drawn like that, here your marks also may get cut. Because the examiner, the paper checker, is having the answer sheet with him, proper figured answer sheet, so this figure is wrong in that case. Because your A and B are not on the opposite side of line DC, they are on the same side of the line DC. The figure is simple, example is simple, still I am telling you again and again, I am explaining you only because you should not miss the figure from the description. This problem is simple, but some other problem you may completely miss the answer, completely wrong figure you may draw, and your answer will be also completely wrong. Okay, so one more practice you have to do, that drawing the correct figure from the given description. Now how will you practice this? Till now whatever examples we have seen, the figure was given and also description was given. So hide the figure and try to draw that figure from the description. You should have practice of this, then check whether your drawn figure and whatever the figure given is correct or not. Only by this method you will get the practice of drawing correct figure from the given description. So let us move ahead to example number 9. Figure is given. Let us read the problem. As shown in the figure, two circles intersect each other in point A and B. In point A and B, these two circles are intersecting. Two tangents touch those circles in point P, Q and RS. Two tangents P, Q and RS, they are touching points. As shown in the figure, line AB intersects segment PQ in C. This line AB intersects PQ in C and RS in D. Show that the C and D are midpoints of segment PQ and RS. We have to show that this side equal to this side and this side equal to this side. So we have to show that C is the midpoint of PQ and D is the midpoint of RS. Very simple example. First look at this circle, bigger circle. This PC is tangent and CD is a secant. So it is intersecting in A and B. So by tangent secant theorem, we already know that PC square is equal to CA into CB. Correct? And now in this circle, we know that CQ square is equal to again CA into CB. Because this secant is common to both the circles. Since right hand side of both the equations is equal, I can write that PC square is equal to CQ square. And hence by taking the square root of both the sides, I can write PC is equal to CQ. So the first part I have proved, PC equal to CQ, very simple. So similarly I can prove the second part. Now we have taken PQ as a tangent, now we will take a RS as a tangent. Now RS as a tangent and this is the secant which is intersecting in B and A. So RD square is equal to DB into DA. Similarly DS square is equal to DB into DA. And hence RD square is equal to DS square. And by taking square root of both the sides, it is RD is equal to DS. So let us go ahead to example number 10. So this is example number 10. The figure is given. The figure is much complicated even to see. So many intersecting lines and so many things are there. But we should simplify the figure in our own mind. Let us read the problem first. In the figure, two circles intersect each other in point A and B. These two circles are intersecting each other in point A and B. Transversals through point A intersect the circle in points P, Q, R and S. There are two transversals through point A, P, Q and RS, which are intersecting this circle into PR and QS. Okay. Line PR and line SQ intersect in T. PR and SQ are extended and they are intersecting in point T. We have to prove two things. First, the PTQ, this angle, and PBQ, this angle, this complete angle, are supplementary. This is what we have to prove. This is the first thing. And second, we have to prove that BSTR is a cyclic quadrilateral. That is B, S, T and R. This is the cyclic quadrilateral that we have to prove. Let us solve the first part, that these two angles are supplementary. Now here, whenever the two intersecting circles are there, whether you want or not, always join this. I join line AB. Now look at this circle, this PBAR. PBAR is a cyclic quadrilateral and hence this angle is equal to this angle. Now this angle R, that is TRS, this angle is the exterior angle of this cyclic quadrilateral, so it is equal to the remote interior angle, that is this angle. Let us look at this circle. Can you see that this is an arc and this angle ASQ, angle ASQ is equal to angle ABQ because angles subtended in same arc. I'll just mark it like this. Correct? So now if you consider this triangle TRS, before that I'll explain it again. First of all, in left side circle, this is a cyclic quadrilateral PRBA and this is the exterior angle R, which is equal to the remote interior angle, that is this angle. Now in this circle, this arc is subtending these two angles. This arc is intersected by these two angles, same angle, so those angles must be congruent, these two angles. Now in triangle TRS, what we have? In triangle TRS, we have this T plus this R plus this S. I am just writing directly T, R and S. Correct? But we know that instead of R you can write this and instead of S you can write this. But this angle is, by the angle addition postulate, we know that this angle is this angle B, PBQ. So T is there, so instead of addition of these two I can write plus PBQ. R is same as this, S is same as this, and by angle addition you can write that PBQ is equal to R plus S. And by a triangle, in this triangle, this is equal to 180 degrees and so this is also equal to 180 degrees. And hence the first part is proved, that is angle T, that is RTQ, is supplementary to PBQ. So these two angles are supplementary is proved by this method. So the first part is over. Now second part. In second part we have to prove that BSTR is a cyclic quadrilateral. BS, I'll just mark by red. B S T this we have to prove that this is a cyclic quadrilateral. Okay, let us prove the second part of the problem, that is prove that BSTR is a cyclic quadrilateral. BSTR is a cyclic quadrilateral. I am using different color pen here. Initially, first we consider that this is a cyclic quadrilateral. Now we will consider that this cyclic quadrilateral. That means in this cyclic quadrilateral, I am drawing it again so that it will be clear, otherwise the figure is very complicated. This is the cyclic quadrilateral and this is external angle. Correct? Now, can you see that this is the arc subtended by this angle, but this arc is also intercepted by this angle. So these two angles are also equal, angles in the same arc. So we know that these two angles are equal because this is the exterior angle. So ultimately I can say that this angle PRB is equal to this interior angle of this cyclic quadrilateral. Now look at what we have to prove. We have to prove that BSTR is a cyclic quadrilateral. We have to prove that BSTR is a cyclic quadrilateral. Now we have to prove this is a cyclic quadrilateral. So now in this quadrilateral, this exterior angle is equal to the remote interior angle, and so by converse of cyclic quadrilateral we can say that this quadrilateral is a cyclic quadrilateral. So it is proved again. I know that the figure is very complicated, two parts are there, but you have to solve one by one part. I don't think that both the part will come for the exam. Either one of the part will come in the exam whenever the figure is very complicated. Always remember, whenever the example or the figures are very tough or very complicated, actually the solution is not that tough. Okay? So here we have proved both the things. In this case I will explain again. In this quadrilateral of this bigger circle, okay, this is the exterior angle, okay, which is equal to the remote interior angle. Now this angle and this angle are equal because both the angles are in the same arc. This is the arc, correct? So these three angles are equal. So this angle equal to this angle. Now we have to prove that this bigger quadrilateral is a cyclic quadrilateral. So in this case we will use the converse of theorem on cyclic quadrilateral. That is, if the exterior angle is equal to the remote interior angle, then the quadrilateral is cyclic, and hence this is the cyclic quadrilateral. Let us go to next example. Problem number 11. The figure is given. The triangle ABC is inscribed in a circle with center O. This is the center O and ABC is inscribed in this circle. Segment AX is the diameter of the circle. AX is the diameter of the circle with radius R. The radius is small r. So we will write that radius is small r. Segment AD is perpendicular to segment BC. This AD is perpendicular to BC. Prove that ABX is similar to ADC. Prove that ABX is similar to ADC. This is the first thing we have to prove. These two triangles are similar, we have to prove. And second thing we have to prove that area of triangle ABC, area of triangle ABC is equal to ABC upon 4R. ABC upon 4R, where this A, B and C are the sides opposite to that angle. That means this BC is A, this AB is C, and AC is B, small b. So this small ABC are the sides opposite to those capital angles. That is, small a is side opposite to capital A, small b side is opposite to capital B angle, and this is C, small c is opposite to this capital C angle. These two things we have to prove that. So first thing first, we will prove this first. Now by looking at the figure, what information we can get? First of all, AX is a diameter. Since AX is a diameter, angle ABX must be 90 degrees because it is the angle inscribed in the semicircle. Okay. Now we have to prove that ABX and ADC are similar triangles. Very simple. First of all, these two are right angles, and I can say that angle X and angle C are angles in same arc. These are the angle inscribed in same arc. Or we can say that this arc is intercepted by these two angles, angle this and angle this. So we can say that angle X equal to angle C, angles in same arc. So by AA test of similarity, triangle ABX and triangle ADC are similar triangles. Now let us go ahead. If angle ABX and ADC are similar triangle, now let us take the ratio AB upon AD is equal to AX upon AC. So since these two triangles are similar, I have taken the corresponding sides and a ratio, and hence just transfer. So AB into AC is equal to AX into AD. Now I will multiply both the sides by BC. AB into AC into BC is equal to AX into AD into BC. Now here AX is a diameter and we are given that radius is R. So I can write here this is equal to 2R into AD into BC, which is equal to AB into AC into BC. We have got this expression. Now what is the area of triangle ABC? Simple, it is 1/2 AD into base BC. It is 1/2 AD into BC. Now we have got two equations. This is the first equation, this is the second equation. Here you can see AB, AC and BC. AB, AC and BC. This is nothing but small a, B into C. A into B into C equal to 2R into AD into BC. But AD into BC we have twice area of ABC. These two will go here. So into twice area of triangle ABC. Now I have to just resubstitute this A, B and C equal to 4R into area of triangle ABC. And so I will shift this 4R here, this side. So area of triangle ABC is equal to ABC upon 4R. Let us understand this once again. First we have proved that these two triangles are similar. Up to this it was very easy. Now after this I have taken the ratios from the similar triangles. AB into AC equal to AX into AD. I have multiplied both the sides because see AB and AC are there. What we wanted here, ABC. We have AB, AC there, but that means A and B in the A. We have AB, that is C is there, AC, that is B is there, but A is not there. Side A is not there here. This small a is not there. So I will multiply both the sides by that. Multiplying both the sides by BC. So here I have got small a, small b, small c equal to 2r. Why 2r? Because the r is the radius and ax is a diameter. So diameter is equal to twice of the radius. So this is equal to 2r into AD into BC. Okay, AD and BC, but AD and BC are in the area of triangle. So from this equation, area of triangle, I can get that AD into BC is equal to twice area of triangle. So here simply I can write ABC is equal to 2r into twice area, 2 into area of triangle ABC. So this is 4r. So ABC upon 4r is equal to area of triangle ABC, which the second statement we have to prove. Okay, let us move to next problem. Let us solve example number 12. The figure is something like this. They are given that ABCD is a cyclic quadrilateral. This ABCD is a cyclic quadrilateral of this smaller circle. Then they said that the line AB and DC intersect in F, and AD and BC intersect in E. Show that the circumcircle of triangle BCF and CDE, circumcircle of triangle BCF, that means this circle, and circumcircle of CDE, that means this circle, these two circles intersect in a point G on line EF. That intersect in the point G on line EF. This is what we have to show. So initially there was only one circle. Okay, this is a cyclic quadrilateral. Now they have extended the lines of the cyclic quadrilateral which meet at point F and point E. And now we have to show that the circumcircle of this triangle and circumcircle of this triangle meet at point G, which is on FE. That means we have to show that if we connect this, we have to show that F, G and E are collinear points, or in short we have to show that these two angles are supplementary angles, or we have to show that FGC and CGE, these two angles addition is 180, supplementary angles, so that these 3 points are collinear point. This is what we have to show. Now let us solve this. BFGC, this is also cyclic quadrilateral when I join this. Okay, so this angle I can say that X is equal to this angle. These two angles are X angle because this is a exterior angle of this quadrilateral. Correct? Now this is the quadrilateral. Now this is the quadrilateral. GCDE is a quadrilateral in this circle. So this angle Y is equal to this exterior angle Y. Correct? Now in this circle, this is a quadrilateral. ABCD is a quadrilateral. It is a cyclic quadrilateral, and so the opposite angles of the cyclic quadrilateral are supplementary. That is, X plus Y is equal to 180, but X plus Y are here also. So this X plus Y is equal to 180 degrees, and since X and Y are adjacent angles, F, G and E, 3 points are collinear points, and hence it is proved that these two circumcircles meet at a point G which lies on FE. Now instead of this XY, if you take the names of the angle, it can be solved, but it becomes complicated again. So either you have to define this x, y, write it here, otherwise you can write the names of the angle A, B, C and so on. Okay. So in this case you have to take two cyclic quadrilaterals first. First of all, this cyclic quadrilateral, prove x equal to x, exterior angle equal to remote interior angle. Then take this quadrilateral, cyclic quadrilateral, so that this exterior angle is equal to this. But these two angles are the opposite angles of the cyclic quadrilateral, this cyclic quadrilateral. So their addition is 180 and hence x plus y is equal to 180. And since these two are the adjacent angles, this G lies on FE. These three are the collinear points. Let us go to next example. Now let us solve example number 13. Prove that the quadrilateral formed by the angle bisectors of a cyclic quadrilateral is also cyclic. That means there is one cyclic quadrilateral. These are the angle bisectors, 4 angle bisectors, and when you extend those, there is one quadrilateral form at the center or inside, not exactly at the center. So we have to prove that if this is a cyclic quadrilateral, then this quadrilateral is also cyclic. Now they have already stated that these are the angle bisectors. So what we will do first? We will first write A, B, B, C, C and D and D. Okay, and let us call this as a P, Q, R, S. And here we will give name as X, Y, Z, T. Okay. Now, how will we solve this? If we can prove that the supplementary angle, that is opposite angles are supplementary, addition is 180, then the quadrilateral is cyclic. That means we have to prove that these two angles or these two angles, but let us say these two angles are supplementary. That we have to prove. How will we prove that? It is actually very simple. First of all, let us understand the figure. What figure says? If this is x, this is also x. If this is z, this is also z. Correct? Now, we will take these two triangles one by one. First, we will take this triangle. Now, a plus b plus x. A plus b plus x is equal to 180 because that is a property of triangle, angle addition. Now, can you see that these two angles are congruent because this is the angle bisector? So can I write, instead of A, can I write the half of the angle S? Half of the angle S, or I can write S by 2. Plus instead of B, I can write P by 2. P by 2 plus X is equal to 180. And similarly, I can write in this triangle R by 2 plus Q by 2 plus Z. This is our 1. Then we have R by 2 plus Q by 2 plus Z is equal to 180 degrees. This is the second equation what we got. So now what we'll get from the first equation? X is equal to 180 minus half of S plus P. Correct? And from 2 we will get Z equal to 180 minus half of R plus Q. If we add these two equations, what we will get? X plus Z is equal to 360 minus half is common and S plus P plus R plus Q. Correct? Now you know that S, P, R, Q, these four angles, this is a cyclic quadrilateral. The addition of any quadrilateral, angles of any quadrilateral is 360 degrees. So here we have 360 minus half of 360. Half of 360 is 180 and 360 minus 180 is equal to 180. So x plus z is equal to 180. So since x plus z equal to 180, the opposite angles are supplementary, addition is 180. So this quadrilateral is a cyclic quadrilateral. Okay, either you can draw figure like this, or you can give proper name PQRS, then give name to this point, let us say ABCD, and then you can write the names of the angle. But again, if that is confusing, you can surely go by this method. Okay, let us go to next example. Let us solve example number 14. The figure is something like this. Let us see what they say. O is the center of the circle. The tangent AC and BD meet at AC and BD meet at point P. Bisectors of these two angles, these are the angle bisectors. These two angles, if AA and BB, these two are the angle bisectors. They meet at point Q. Now they are given if APB is 60 degrees, APB, if this angle is 60 degrees, prove that angle PAB and QAB, angle PAB and QAB are congruent. Triangle PAB is congruent to triangle QAB. Not very difficult. How will proceed? First, analyze the figure. We have already written the congruent angles. Now these are the tangent segments, those are equal. Now if these two tangent segments are equal, this has automatically become isosceles triangle. And if this angle is 60 degrees, then these two angles which are same, I will write here C and C, these two angles are congruent, C and C. If these two angles are congruent because of the base angles of the isosceles triangles, then this must be equal to 60 and 60, both. So now this triangle has become equilateral triangle. Let us see, this QA is secant and AC is the tangent. So angle A must be equal to angle B, because tangent secant theorem, the angles in same arc. Correct? That means this is also angle A, this is also angle A. If this is angle A, since this is the angle bisector, this will also become angle A. Right? Now, if this is angle 2A, this is the exterior angle of this triangle. So this angle, this complete angle is 120 degrees. This complete angle is 120 degrees. Because these are the angles in linear pair. If this is 60, this is 120. And since this is angle bisector, both the angles are A, these are also 60 degrees, and hence all the angles are 60 degrees. Correct? Now this is also isosceles triangle. But since base angles are 60 degrees, this becomes equilateral triangle. So now both of these triangles are equilateral triangles. Correct? Now this side is common to both the triangles. And since they are equilateral triangle, other sides must be congruent. And hence triangle BQA and ABP are congruent triangles. First of all, you have to prove that those are equilateral triangles. And then you should say that since in these two equilateral triangles, one side is common, that means all sides are equal, and hence these two triangles are congruent. You can put any test like SSS or AAA, whatever test you want to put, you can put here, and these two triangles are congruent. Simple example. Let us go to next example. Let us solve example number 15 of problem set 2. If all the sides of a quadrilateral are produced in a same order. That means either clockwise or anti-clockwise. Now PQRS is a quadrilateral. They say that show that the quadrilateral formed by the bisectors of the exterior angle is cyclic. That means we have to prove that. Now let us see the figure again. PQRS is a quadrilateral. I have extended these sides. Okay. Now these exterior angles, if you take the angle bisectors of these exterior angles, they form one quadrilateral. We have to prove that this quadrilateral in the red one is a cyclic. Okay. Let us see how can we prove this. Actually we have seen such example previously where that quadrilateral was inside the cyclic quadrilateral, but now it is outside. Okay. We have taken the exterior angles, correct? Now, since these are the angle bisectors, I can say that x x y y z z, I can say m m. Okay. Now we will consider only two triangles, one this triangle and second this triangle. In the previous example also we have taken two triangles. Okay, here also we will take two triangles. Now can you see that these are the intersecting lines? So this angle is also y, correct? And this angle is also m. Now in this triangle we have angle A plus angle x plus y is equal to 180 degrees, correct? But what is x? X is half of this exterior angle P, correct? So I will write x plus P by 2 plus what is y? Y is the half of this exterior angle Q. Q by 2 is equal to 180. And similarly in this triangle we have C plus half of this is M and this is also M. So half of this exterior angle S, C plus S upon 2 plus this R upon 2 is equal to 180. The equation is exactly similar to our previous example's equation. From this first equation I will get A is equal to 180 minus 1 upon 2 P plus Q. These two will go there. And from here we will get C is equal to 180 minus 1 upon 2 S plus R. When you add these two equations, what we will get? A plus C, angle A plus angle C, I am not writing angle sign here. A plus C is equal to 360 minus 1 upon 2 P plus Q plus R plus S. But we know that the addition of all the exterior angle of a quadrilateral is 360. So we have 360 minus half of 360, which is equal to 180. So now we have got A plus C equal to 180. Angle A plus angle C equal to 180. Now in this quadrilateral ABCD, in this quadrilateral, if the opposite angles are supplementary, that is addition is 180 degrees, then this quadrilateral is a cyclic quadrilateral. It is proved. So first of all, you remember one thing, we are just discussing all the examples here. I am not actually writing the example step by step. All these things writing in a steps you have to do. Okay. So this quadrilateral is proved. Now one more thing, I am writing this with the red pen, but you should not use any colored pen in the paper. You have to use only pencil and only one color pen, blue color pen. Don't use this red. I have just used red color to show the difference in the figure. Okay, you have to draw the figures and write everything in a proper blue pen. no color pen is allowed in exam, correct? So you have to write all these steps properly, okay? Either you can use the same method like x, x, y, y, something like this, or you can give name and you can write the name of the angle properly. For that, writing the name of the angles properly, you have to take here also something, M, then N, take extended lines, M, N, O, and let us say L, and then you can write the names of the angles properly. But you can adopt this method also. So let us go to next example. Let us see example number 16. In an isosceles triangle PQR, the vertical angle P is 50 degrees. There is one isosceles triangle. PQR, PQ and R, this angle is 50 degrees. Then the circle passing through Q and R intersects PQ in S and PR in T. Now there is one circle which is passing through these 2 points, okay, which intersects PQ in S, and this in T. ST is joined. Now we have to join ST. My figure is not very proper because I have drawn by rough hand. You have to draw proper circle and proper figure, okay? Even the rough figure should be proper, should be drawn with the proper pro circle and proper scale. We have to find angle PST. We have to find this angle PST. This angle is to be found out. Okay? Very simple. Since this is isosceles triangle, these both the angles are equal. Correct? If this angle is 50, then 180 minus 50 is 130, and since both the angles are same, both the angles are of 65 degrees. Now this is a cyclic quadrilateral. PQRTS is a cyclic quadrilateral. So by the external angle theorem of the cyclic quadrilateral, this angle is also 65 degrees. That means this exterior angle is equal to the remote interior angle. This is the property of cyclic quadrilateral. A theorem we have already seen. So by this external angle theorem of cyclic quadrilateral, we have angle PST is 65 degrees. It is proved. Very simple. Let us go to next example. Let us solve example number 17. Quadrilateral ABCD is a parallelogram. Let us draw one parallelogram. So this ABCD is a parallelogram. A, B, C and D. A circle passing through D, A and B. A circle is passing through D, A and B. Intersects BC in the point P. So let us draw one circle. I am drawing rough circle. It doesn't look like a circle. Assume it. It intersects in P. Okay. What they say? Prove that DC equal to DP. Prove that DC equal to DP. This is what we have to prove. Let us see how to prove this. Now here we have to prove that DC equal to DP. That means this DP we have to join. And we have to prove that this DP equal to DC. Not very difficult. Let us see. This angle and this angle are equal because this is a cyclic quadrilateral now, and by the exterior angle theorem of cyclic quadrilateral, angle A and this angle P are equal. But ABCD is a parallelogram and opposite angles of the parallelogram are equal. So this angle, if I call this angle as X, this is X and this is also X. If these two angles in this triangle DPC, if these two angles are same, congruent, then this becomes isosceles triangle. And when these base angles are same or congruent, in that case this DPC becomes an isosceles triangle and opposite sides of the congruent angles are congruent, and hence DP is congruent, DP is equal to DC. This is what we proved. So generally we have to use the exterior angle theorems at lot of places. But remember, though this is a circle, the parallelogram properties also you should know. Correct? Let us move to next example, number 18. In a cyclic quadrilateral ABCD, ABCD is a cyclic quadrilateral. The bisectors of opposite angle A and C. This AP is a bisector of angle A and this CO is a bisector of angle C. Okay? Meets the circle in P and Q. These bisectors meet at P and Q. This is Q. So they meet the circle at P and Q. Prove that PQ is a diameter of this circle. We have to prove that this PQ is a diameter of the circle. Now, I have written X and X, okay, and Y and Y because these are the angle bisectors. We know that this is a cyclic quadrilateral. We know that this angle A plus angle C is equal to 180 degrees. So angle A plus C is equal to 180 degrees, but A is nothing but 2x. So 2x plus 2y, 2x plus 2y is equal to 180 degrees. Now this is an angle inscribed in this arc BP. So what will be the measure of this arc BP? Is double of this, that is 2x. And this y is an angle inscribed in this arc. So what will be the measure of this arc BAQ? Is double of this, 2y. So now for QP, this is 2x plus 2y equal to 180 degrees. That means this QABP is 180 degrees. That is, this is semicircle, and hence QP is the diameter of this circle. Again I am telling you, these both the angles are equal, these both the angles are equal as they are angle bisectors. Correct? Now opposite angles of the cyclic quadrilateral are supplementary, so A plus C is equal to 180. So instead of A I can write x plus x, that is 2x. And instead of C, I can write y plus y, that is 2y. So 2x plus 2y is equal to 180. But what are the measure of this arc? This is the angle. This arc is intercepted by this angle. So the measure of this arc is 2x and measure of this arc is 2y, because this is the angle and this is the arc here. So now by the addition of the measure of arcs, 2x plus 2y, okay, this is nothing but 180 degrees, which is a semicircle, and so PQ is diameter of this circle. It is proved. Before going to next example, let me tell you that there is one more method of solving this. Okay, instead of arc additions, what you can say, you join this. Okay, now you have already measured this arc as 180 degrees, but now this is the angle inscribed in this arc. Correct? An angle inscribed in a semicircle is 90 degrees, and hence this is the diameter of a circle. Both the way it is possible. Okay, so you can write the explanation in whichever way you want. Let us go to next example. The example number 19. Very simple example. Prove that in a cyclic trapezium, angles at the base are congruent. Cyclic trapezium, circle is there and trapezium is there, whereas opposite sides are parallel. Now this is a cyclic trapezium, opposite sides are parallel, so AB is parallel to DC because it's a trapezium. What they say? Prove that in cyclic trapezium, angles at the bases are congruent. That means we have to prove that angle A and angle B are congruent and angle C and angle D are congruent. Let us prove that first angle A and B are congruent. Now since this is a cyclic trapezium, or we can call it as a cyclic quadrilateral, so D and B, D plus B is equal to 180 degrees because in cyclic quadrilateral opposite angles are supplementary. Now it is already given it is a trapezium, that means AB parallel to DC and AD is a transversal, and hence this angle A, interior angles are also supplementary. So angle D plus angle A is equal to also 180 degrees. Correct? And hence we can say that from 1 and 2, A is equal to B. 180, 180, so D plus B is equal to D plus A. D will get cancelled and we will get angle A is equal to angle B. And hence the base angles are congruent. And similar way you can prove that D and C are congruent. So this is very easy example. Let us go to next example. I am not going to solve the example number 20th as it is exactly similar to example number 8 of this problem set. Okay, the two circles intersect each other in a points A and B. The two circles are there, and this example is exactly similar to your example number 8. So no need to solve it here. Please refer to previous example. Let us see next example. In triangle ABC, P, Q and R are the midpoints of sides AB, AC and BC. So first of all, let us draw triangle ABC. So in triangle ABC, PQR are the midpoints of the sides respectively, and AS is perpendicular to BC. This AS is perpendicular to BC. Prove that PQRS is a cyclic quadrilateral. We have to prove that P, Q, R and S. So you have to join this. So we have to prove that, rather we'll draw it by red pen. So we have to prove that this is a cyclic quadrilateral. This is what we have to prove. Now in this case, in this triangle, P and Q are the midpoint of the sides, and hence by midpoint theorem, first of all, PQ and BC, PQ and BC are parallel. This is the first, and by second, PQ is half of BC. PQ is half of BC, but R is the midpoint. So PQ is equal to BR. So we have PQ is equal to BR. Okay. Now in this parallelogram, this is the parallelogram, these two sides are parallel, opposite sides are parallel. PQRB has become a parallelogram now, correct? And hence this angle x is equal to this angle x. Correct? Opposite angles of the parallelogram are congruent. Now you consider this triangle ASB. This is a right angle triangle. But P is the midpoint. So PS is the median on hypotenuse. PS is the median on hypotenuse, and hence this PS is half of AB. But what is half of AB? Half of AB is same as BP. So these two sides are equal. Right? And so this angle is also X. Now this angle is X, this angle is X, and we have this quadrilateral. So this has become the exterior angle of the quadrilateral. And if the exterior angle of the quadrilateral is equal to the remote interior angle, in that case that quadrilateral is cyclic quadrilateral. This is the converse of the theorem which we have on the cyclic quadrilateral. And so PQRS is cyclic quadrilateral. It is proved. Let us go to next example. Problem number 22. Triangle ABC is inscribed in a circle. This triangle is inscribed in this circle. We don't have the center point of the circle. Point P lies on the circumference. Now here is the point P which lies on the circumference of this circle. Through P, PN, PM and PL are the perpendicular on the sides of the triangle. Now from this we have drawn the perpendiculars on the sides of the triangle. Let us draw the perpendiculars on the sides. Now we will first join these lines. Now first we have to understand what the problem is. Let us see the problem again. ABC is inscribed in a circle. From P is on the circle. We have drawn the perpendiculars to all three sides. Now we have to prove that this N, M and L are collinear points. This is what we have to prove. Let us solve something like this. Okay. First, consider this quadrilateral. PMAN. This is right angle, this is right angle. Opposite angles are supplementary, and hence this is a cyclic quadrilateral. That means a circle passes through all these vertices, and hence PMN and PAN, these are the angles in same arc. Correct? If this circle is passing, can you see that these 2 points and these 2 points, the same circle is passing through this. So angle PMN is congruent to angle PAN. Correct? I will mark this angle as X for simplicity. Now consider quadrilateral PABC. This is a cyclic quadrilateral because all the vertices on the circle, and now here this X is the exterior angle of this quadrilateral, cyclic quadrilateral, which is equal to the remote interior angle, so that this is angle X. Now check this. This angle 90 is given. PMC, this angle 90 is given, and this also angle 90 is given. But both of these angles are in the same arc. Correct? And those are given as 90, and hence this quadrilateral is a cyclic quadrilateral. This quadrilateral has become a cyclic quadrilateral now. And now this angle plus X is equal to 180, opposite angles of cyclic quadrilateral. Let us say this angle is Y. So X plus Y is equal to 180. But this is also X, here is also X plus Y, and this is a straight line. These are the angles of the linear pair. these are the angles of the linear pairs x plus y, and so these two angles are the angles of the linear pair because the addition is 180, and hence this line NML is a one and same line, and hence N, M and L are collinear points. It is little bit complicated to understand, and these kind of problem you have to solve again and again so that it will be fit in your mind, because the figure is complicated and problem is also a little bit complicated. I will explain it again. The first of all, the figure you know, what figure is you know. First of all, PMAN, this is a cyclic quadrilateral, and this angle x is equal to this angle, because those are the angles in same arc. Now in PABC, this bigger quadrilateral, it is a cyclic quadrilateral, so this is a exterior angle which is equal to the remote angle. Okay, now this angle and this angle which are given 90 degrees, but they are in the same arc. These two angles are in the same arc, so this is a cyclic quadrilateral. This PMLC is a cyclic quadrilateral, correct? And this angle x, which we have already proved equal to this x, x plus y is equal to 180, and so this x plus y is also equal to 180. And since those are the angles in linear pair, so this line is straight line, so N, M and L are collinear points. So you have to solve this problem again and again. That means you have to write this problem without watching your previous answer again. Only then you will be able to solve such kind of problems. These are little bit complicated problems. Only key is solve again and again. That's all. So let us go to the last example of problem set 2, that is 23rd example. In triangle ABC, segment AB and AC are congruent segment. So let us draw triangle ABC. Triangle ABC, whereas AB and AC are the congruent. Then they say that P is any point on side AC. Let us consider P is some point on AC. Through the point C, line is drawn to intersect BP produced. This BP line is extended here. This is our point P. So here we have produced one line, and this is our point Q. Now this line, this CQ is drawn such that the angle ABQ is equal to angle ACQ. Angle ABQ, this angle, is equal to angle ACQ, this angle. If this is X, this is also X. We have to prove that angle AQC is equal to 90 plus half of angle BAC. So now here we have to prove that angle AQC, this angle AQC is equal to 90 plus half of BAC, this angle. And we are concerned with these two angles. We have to prove that this angle is equal to 90 plus half of angle BAC. Now just pay attention here. When we extend this AQ subtends congruent angles, because this X and this X, ABQ and ACQ, that means this line AQ is subtends congruent angles, and hence ABCQ is a cyclic quadrilateral, correct? And in cyclic quadrilateral, we know that angle B and angle Q are supplementary angles. So let us write that angle AQC plus angle ABC is equal to 180 degrees. So we have got this as our first statement. Now in this triangle we know that these two sides are congruent. They are given, it is isosceles triangle. So angle B and angle C are congruent angles. Correct? So let us write that this angle A, I will call this as let us write this as angle A, this complete as angle B, and this complete as angle C. Okay, let us call it. So angle A plus B plus C is equal to 180. But angle B and angle C are congruent. So here instead of C I can write angle B. Correct? So I will write that angle A plus 2B is equal to 180. AQC I already got here in the equation 1. ABC, that is angle B, that we have to substitute here. So what is angle B is equal to 180 minus A upon 2. So by further solving this I will get B is equal to 90 minus half of angle A means this angle BAC. This is my 2. Can we substitute here? If we substitute in the values from equation 2 to equation 1, this angle B is also nothing but angle ABC. Correct? So angle ABC is equal to 90 minus half of angle BAC. So we will substitute there and let us see what we get. So I will write it here. So angle AQC, now our equation becomes plus angle ABC is 90 minus half of angle BAC is equal to 180. So let us take everything on that side. So that is what we have to prove. So angle AQC is equal to 180 minus 90 plus half of angle BAC. 180 minus 90 is 90 plus half of angle BAC. So angle AQC is equal to 90 plus half of angle BAC, which is proved. Let me explain you this again. This is a triangle whereas two sides are congruent. Then we have extended, there is some point P and we have extended BP and we have drawn CQ in such a way that angle ABQ and ACQ are congruent. This AQ is subtending two congruent angles and hence this ABCQ is a cyclic quadrilateral. Now when this ABCQ is a cyclic quadrilateral, that means opposite angles are supplementary. That means the first equation we got, AQC plus ABC is equal to 180. Okay? Now consider this triangle. In this triangle, these three main angles addition is 180. So I am considering this AB. Deliberately I said ABC because I don't want to write the names of the angles. We'll write it later. Okay. So angle A plus B plus C is equal to 180. But B and C are congruent angle. Why? Because this is isosceles triangle. So instead of C I can write B. So I written A plus 2B is equal to 180. And so B is equal to, that is angle ABC equal to 90 minus half of BAC. So the first equation we have got, we had to prove angle AQC. So AQC I got. ABC I have to replace with the here. BAC I want here. So now I will replace of values from the equation 2 into equation 1 here. So angle AQC plus I have to replace this value. So plus 90 minus angle BAC is equal to 180 degrees. Solving this, we will get angle AQC is equal to 90 plus angle BAC, which is proved. So with this example, we are hereby finishing problem set 2 and also the chapter number 2, circle. Thank you very much.